So welcome to this Qest session on learning and verification. So we have 3 talks in this session. Each of them has a 20-minute pre-recorded video and then a 5-minute Q&A with one of the authors. So we'll get started straight away. The first paper in this session is called DSMC Evaluation Stages, Fostering Robust and Safe Behavior in Deep Reinforcement Learning. And the author here is Timo Gross. So can we start the first video, please?
Welcome to the presentation of our paper DSMC Evaluation Stages, Fostering Robust and Safe Behavior in Deep Reinforcement Learning. My name is Timo Gross, and this is joint work with Daniel Höller, Jörg Hoffmann, Michaela Klaug, Hendrik Meerkamp and Verena Wolf. In recent years, neural networks, especially deep neural networks, have accomplished major successes around many computer science domains. To name just a few, there have been breakthroughs when it comes to playing chess or solving problems like the Rubik's Cube. Further, we see the usage in real-world examples such as robotics or autonomous driving. Despite its success, however, DRL technology is not without fail, especially in safety-critical applications. The first deficiency we would like to emphasize here is the lack of robustness. The performance of deep reinforcement learning agents is measured in average rewards as optimized by the DRL training. Such an exemplary training plot can be seen here. That, however, may average out poor local behavior, which can be seen when looking at the maps on the right. This is one example of the racetrack benchmark, a very simple race car simulation, which we use in our paper. While the overall performance can be considered okay, we here depict the average reward per starting point. As one can see, especially on the bottom and in this blind alley, the performance is far away from the optimal solution. Further, the existence of both green and red regions indicates high variance. The second deficiency we address is the usage of degenerated reward structures. When it comes to objectives targeting safety, especially for the natural objective to maximize the probability of reaching a goal condition, this yields rewards 1 in goal states and 0 elsewhere. This extremely sparse reward structure is not suited for DRL learning in large state spaces. Hence, to identify a useful policy, proxy objective, such as discounted cumulative reward, giving positive feedback for goal states and highly negative feedback for unsafe states, must be used. The upper plot here is the one we have already seen, while the underlying one here depicts the goal reaching probability from every position on the grid. It might look similar on the first side, but it actually has a different scale and cannot directly be compared to another. While we of course somehow expect that the reward correlates with the goal reaching probability, crashes are more tolerable in the reward structure. As this is difficult to see, additionally take into account this plot on the right, where we depict the goal reaching probability for the standard DRL method deep Q learning and ERPG, which is one of the methods we are about to introduce. ERPG directly takes goal probability into account, which clearly pays off. To list our contributions, we introduce evaluation stages, which are conducted at regular intervals during training and which determine regions of the state space with weak performance. We use recent work of deep statistical model checking to examine properties. We further introduce a feedback loop between these evaluation stages and the deep reinforcement learning algorithm. Also, we introduce 2 different methods to do so. As our method is built upon deep reinforcement learning, let's have a close look what the principle of RL is. In reinforcement learning, an agent learns through interacting with the environment. In particular, the agent receives information from the environment about the current state, then decides upon an action to take, and receives a reward and the information whether the current episode has terminated. The objective we would like to maximize is the so-called return, the accumulation of all returns R that were observed. To make short-term rewards more important than long-term ones, a discount factor gamma smaller than 1 may be used. While our methods can in principle be used in any DIL algorithm, we here introduce it based upon deep Q-learning. In Q-learning, the idea is to use this interacting scheme that we just saw to learn the so-called Q-values. These Q-values represent the expected return, that is the expected accumulated discounted reward, when being in state S and taking action A. In classical Q-learning, each of the Q-values was learned separately by having a single entry in a table. For deep Q-learning, we train a neural network that approximates all the Q-values. Let's have a short look at the classical deep Q-learning algorithm. In deep Q-learning, where we train for m episodes with a length of at most t steps, we act epsilon greedy. That means, with a chance of 1 minus epsilon, we take the decision of the policy that is induced by our current neural network. Otherwise, we take a random action to explore the state space. We then follow the scheme we just saw. We perform the action and observe the reward and the following state. This observation, state, action, reward, and next state, is then saved in a replay buffer. Every c steps, we sample a mini batch from that buffer and calculate the loss. The loss between the target, which is the observed reward, and our approximation of the Q value for the next state, and our current estimation of the actual Q value. With that loss, we can perform a gradient descent step to minimize the difference between the observation and the approximation of our Q values. Note that the replay buffer is an important aspect of deep Q learning that is used to break the correlation between the samples. If we would directly learn from the samples, the gradient descent assumption of IID data would be harmed. Thus, we store the observations in a buffer and then learn by mini batches sampled from said buffer. Without going into further details, it should also be mentioned that another important aspect is the so-called target network, which means that the network which is used to compute the target is not identical to the network used to generate samples, but it is an older version of it. This modification makes deep Q learning more stable. One common improvement of the deep Q learning algorithm is the so-called prioritized replay. Here, for every generated sample, we compute a priority which reflects the loss for the current sample. When sampling from the replay buffer, we do not further sample uniformly, but according to the priorities. Thus, we sample more from examples with a higher loss, which means we sample more from such observations that can be learned from more. In the following, we will abbreviate deep Q learning with prioritized replay as DQNPR. In the algorithm, that change is rather small. We store the priority delta along with the observation in the buffer and sample from the buffer according to set priority. So now that we had a look at the algorithm we are about to extend, we can start with some definitions or notations we will need. We define a partition of the set of initial states I into regions J, such that none of the regions is empty, the regions are disjunct, and all initial states are contained within one region. We additionally assume that there is one representative state per region. Also, we define an initial probability distribution for regions by making use of the value of the initial distribution of the underlying MDP for the representative. In general, an evaluation function may be any function that maps from the partitioning to values within 0 and 1. In particular, we will map the value of the representative to its whole region. We define an evaluation stage to be the calculation of the evaluation function for all regions. The first method we propose here is the so-called evaluation-based initial distribution EID. The idea is to use the insights gained through the calculation of the evaluation stage. We would like to start more often in regions where the local performance is bad. Instead of sampling according to the initial distribution of the MDP, we shift the initial distribution. By multiplying the distribution of the regions with 1 minus the value of the evaluation function, we start less where the evaluation value was good and vice versa. Within the regions, we sample uniformly. Algorithmically, we first need to introduce the evaluation stage. That means after a threshold of p initial episodes of usual deep Q learning, we perform an evaluation stage every L episodes where we compute and store the evaluation value of each region. Afterwards, we sample the initial states of each training episode according to set value as just presented. Evaluation-based prioritized replay (EPR) follows an idea similar to deep Q learning with prioritized replay. But instead of computing the priority according to the loss of the current sample, we compute the priorities based on the value of the evaluation stage. This is especially helpful considering deficiency 2, where the objective landform is different than the desired one. The latter can then be expressed by the evaluation function. Note that we don't only have initial state, but also state that are visited within an episode. As we only compute the evaluation for initial states, we use the priority of the states that the training episode was started in instead. In the algorithm, we of course need to keep the evaluation stage. The only change compared to DQNPR is how we compute the delta, the priority. The benchmark we evaluate our approach upon is the so-called racetrack, a commonly used AI and deep reinforcement learning benchmark. The racetrack is a very simple race car simulation played on a grid given through a map. The state is uniquely described through the two-dimensional position and the also two-dimensional velocity. For learning purposes, we additionally provide 11 features representing distances to the walls and to the goal line. In each step, an action which represents the discrete two-dimensional acceleration within 1, 0 and -1 is chosen. This results in 9 different applicable actions. Additionally, we assume a slippery road. That means with a certain probability, the action, which is the acceleration, may fail and then the velocity remains unchanged. The reward function we used was optimized empirically. We give a positive reward if the agent wins the game and a high negative reward if the agent loses the game. Additionally, we give a small negative reward if the state remains unchanged, which means the car is standing still and deciding not to do anything, to prevent the agent from not doing anything at all. For every other state where the game is still ongoing, we give a reward of 0. The maps we evaluate upon are displayed here. Bar-to-Big, which was already frequently used in literature, and 2 new maps, Maze and River, which are more challenging due to their structure. We used 2 different evaluation functions. The expected return, which is the same objective we learn from, abbreviated EIDR and EPRR, respectively, and the goal reaching probability, which is computed by using deep statistical model checking, abbreviated EIDG and ERPG, respectively. We compare ourselves to both DQN and DQN-PR. For the racetrack maps, we considered each map cell to be a region, and thus the representative is the position of the map cell with 0 velocity. We use a 10% noise level for the river map, which is already quite difficult due to its structure, and a very high noise level of 50% for the Bar-to-Big and Maze map. Also, it is known that DRL results are sensitive for different random seeds, which is why the results we report about are averaged over several runs. We now turn our attention to the first efficiency, local robustness. As can be clearly observed, the DQN and the DQN-PR method perform quite good overall, but there are some areas of the state space where the performance is locally not good. The EIDR and EPRR method, in contrast, have an increased return in that regions without suffering in the other ones. We call that due to the noise, a perfect solution is impossible. This claim can be strengthened when looking at the variance of the return for all methods. Except for the bar-to-big map, which is the easiest task here, the variance of EIDR and EPRR is significantly decreased compared to DQN and DQNPR. The improved local robustness does not only reduce the variance, but it also improves the overall performance, which can be seen when looking at the overall average return. The reason of the increased performance and decreased variance can be explained in the training. We here show how often each cell was encountered during the training of the river map. One can clearly observe that the problematic areas are visited more often when using EIDR or ERPR than when using DQN or DQN-PR. Turning to the second deficiency, we first would like to point out what we call the interesting regions of the map, where the car is not able to navigate to the goal directly, but first somehow has to turn around. Especially with a high level of noise, this is a challenging task. When we compare the goal reaching probability for the entire map, we once again see not much of a difference for the bar-to-big map, but a clearly increased goal reaching probability of EIDG and ERPG compared to DQN and DQNPR. This becomes even more clear when looking at the just presented interesting regions only. Note that EIDG and EPRG both outperform DQN and DQNPR, but we cannot clearly conclude which of our both new methods is better. To conclude, we today pointed out two deficiencies which are omnipresent in deep reinforcement learning. First, the lack of local robustness, and second, degenerated reward structures having the need for proxy objectives. We shortly introduced deep Q learning as one possible deep reinforcement learning algorithm which we used to implement evaluation stages. We introduced these evaluation stages into the algorithm by proposing two different methods: evaluation-based initial distribution and evaluation-based experience replay. Afterward, we made experiments that show that both of our methods can lead to, first, a decreased variance and increased overall performance when considering the return, so the objective that was learned upon. And second, an increased goal reaching probability when it comes to altering the objective such that it is suited for learning. Therefore, we conclude that both of our proposed methods are suited to address both of the exposed deficiencies. Thank you for listening, and now I'm happy to answer your questions.
Okay, great. Thanks, Timo, for the nice presentation. So as is said in the chat, if you do have questions, please either raise your hand or you can use the Q&A and I will pass them on. Right, so we have the first question that's come in. This is from Alessandro. So would it be possible to extend the presented approach to continuous state or action MDPs?
Yes, it would be. So for the first of the proposed methods, the EID, it's possible to extend them to any DRL algorithm, while for the EPR, it's possible for every DRL algorithm which uses a replay buffer, because we need to replay buffer to set priorities there.
Okay, thank you. Do we have any further questions? Let me just check. So one simple question. I wasn't sure whether you're using the neural network for the policy or the value function. Does it make a difference which you do for your method?
We use the neural network to approximate the Q values, and the policy is then simply given by taking deterministically the highest Q value there is for every state.
So this would, by the way, be a difference if we use continuous action space, then the neural network is used differently. But this is the same for the other algorithm we extend. So this would not be much of a change of our algorithm. But the main difference, as mentioned, which also inherits from deep Q learning, is that we have two neural networks. One neural network we use for currently acting in the environment and so creating observations, and the other neural network is used to update the Q values. And then we always perform a soft update to bring these networks closer together to have a more stable learning process.
Okay, thank you. Okay, do we have any additional questions? So one more kind of quite general question for me. So you mentioned you used deep statistical model checking. So, I mean, I'm not really familiar with that. Can you just say a few more words about how that technique works and kind of why it integrates nicely with what you're doing here?
The deep statistical model checking uses Monte Carlo simulation runs to approximate the goal reaching probability within the MDP, within any game which is spanned through an MDP, by using the neural network as basically a magic toolbox to break the non-determinism there and to select the actions. So it gives us, with a certain probability we fix, the exact goal reaching probability we would like to have. Okay, so it could be any kind of black box way of simulating the system, really, it doesn't matter. Yeah, exactly. In general, you could take any evaluation function you would like, but the goal reaching probability and therefore DSMC is so interesting because if we use exactly that objective to learn, the policies that result are really bad because they cannot learn from that reward structure. And therefore, it is interesting to say, okay, we learn from this one reward structure we can learn from, but we originally would like to have a look at the other reward structure, which we then can analyze by using DSMC. Okay, I see. Thank you. So we probably can squeeze in one more question if anyone has last chance for any questions. Okay, I don't think we have further questions now, but you are obviously welcome to talk to the author after the session, either here or on Gather. Okay, so thanks again, Timo, much appreciated. We will now move on to the second presentation. So the second paper is titled Active and Sparse Methods in Smooth Model Checking, and the author who's here is Paul Piho. So can we start the second video, please? And we'll move on to the third and final talk in this session. So the third paper is titled Safe Learning for Near Optimal Scheduling. And the author who's here is Debraj Chakraborty. So let's start the video, please.
Hello, I am Debraj Chakraborty and I will talk about our work on safe learning for near optimal scheduling. This is a joint work with Damia Busato Gaston, Shivashish Guho, Guillermo E. Perez, and João-François Raskin. A task system is a set of tasks partitioned in hard and soft tasks. Each task in the system generates an infinite number of instances called jobs. The tasks are preemptible. That means the scheduler can stall one job and continue another job. Formally, a task is a tuple of the form C, D, and A, where D is the relative deadline of jobs generated by the task, C is a discrete probability distribution over possible computation times of all these jobs, and A is the distribution over possible inter-arrival times of these jobs. The difference between hard and soft tasks is that hard tasks should not miss a deadline. The soft task can miss a deadline, but that would result in a penalty or cost. We model a task system as a Markov decision process or MDP. It is a directed graph containing two kinds of vertices, square vertices and circle vertices. We can also think it as a game where player 1 is controlling the square vertices and player 2 is controlling the circle vertices. Each vertices represent the state of the system. Each edge from player 1 vertices are labeled by an action. The edges from player 2 vertices have an associated cost. The player 2 vertices also have an associated probability distribution on the edges coming from them. For example, starting from S0, player 1 have two actions to choose from. Suppose it took action A1. Then from S1 with probability 2/3, the next state will be S3, and with probability 1/3, it will be S4. Suppose the state evolves to S3, so the associated cost is 2. Now again we have action A3. And with probability half, the state changes to S4 and total cost becomes 3. And so on. Now this creates a play of an MDP. Mean cost of a play is the average cost we get in this play at the limit. A strategy for player 1 is a function from paths ending with player 1 vertices to available actions. For example, here a strategy will dictate if player 1 would play action A1 or A2 from S0. Fixing a strategy in MDP creates the Markov chain. Expected mean cost of a strategy is the expectation of the mean cost in the Markov chain created by the strategy. Let us give an example how we can create an MDP for the task system. Consider this task system with two tasks, one hard and one soft. The deadline for both tasks are 2 time units. For both tasks, the inter-arrival time is 3 time units with probability 1. The hard task takes 1 time unit to complete, while the soft task complete in 1 time unit with probability 0.4 and 2 time units with probability 0.6. A state of the MDP would contain the following information: the remaining time to the deadline, a distribution over possible remaining computation time, a distribution over possible times before next arrival of a job of that task. So for example, this is what the initial state would look like. The two players correspond respectively to the scheduler and the task generator. At their state, the scheduler can either choose an active task and give it one CPU time unit for execution or can stay idle. The task generator has 4 possible actions: do nothing, finish the current job, submit a new job, or kill a job by a soft task and submit a new one. Then we update the next states accordingly. We describe part of the MDP here. We start from the initial state, which is controlled by the scheduler. It has 3 options: schedule the soft task for 1 time unit, or schedule the hard task for 1 time unit, or do nothing. If the soft task is scheduled for 1 time unit, now the next state is controlled by the task generator. Here for the hard task, the remaining computation time is still 1 as the task has not started yet. But the deadline and next arrival time is decreased by 1 time unit. Same for the deadline and next arrival time of the soft task. As the job of this task ran for 1 time unit, now the computation time for it is 0 with probability 0.4 and 1 with probability 0.6. So task generator will finish the soft task job with probability 0.4 and with probability 0.6 it goes to a new state with remaining computation time 1. Then suppose the scheduler stalls the soft task and schedules and finishes the hard task. Now the soft task misses its deadline, so the scheduler cannot schedule it anymore. When new job arrives, the task generator submits them and kill old jobs. Here we add the cost 10 for missing the deadline for the soft task. Similarly, we have more states in other paths. Also in this path, when the scheduler doesn't schedule the hard task job at all, we see that the hard task misses its deadline. Then we go to a special sync state, and here we put a big danger sign on it, which is the bad state our system needs to avoid. Our objective would be to find a strategy that avoids deadline misses by the hard task and minimizes the expected mean cost of the deadline misses by the soft tasks. This can be done this way. We prune the MDP to obtain the safe region by removing all those vertices from which the scheduler doesn't have a strategy ensuring safety. This can be done in polynomial time of the size of the MDP. This safe region is a smaller MDP, and we find the strategy that minimizes the expected mean cost in the safe region. In practice, this is done by value iteration algorithm, which is implemented in probabilistic model checking tools like Storm. We consider a practical setting in which only the deadline and the domains of the distributions describing the tasks of the system are known a priori, and not the exact distributions for execution and interval time. In this case, we need to learn the model by sampling and then compute a near optimal safe strategy from the learned model. We call two distributions P and Q epsilon close if PA and QA are epsilon close for all A in their domain. Now let us talk about what kind of learning guarantees we can get. Given a class of task systems, we say that the class is probably approximately correct or PAC if there is an algorithm L such that for all task systems T in this class, for all epsilon and gamma, if we are given the structure of T, we can compute an epsilon closed task system with probability at least 1 minus gamma. The class is safely PAC learnable if it is PAC learnable and the algorithm L can ensure safety for the hard task while computing the approximation. And the class is efficiently PAC learnable if it is PAC learnable and there is a polynomial Q in the size of the task system 1 by epsilon and 1 by gamma such that L computes the approximation in time bounded by Q. So how would we learn an unknown distribution P? We collect samples according to the distribution. If we collect enough samples, the relative frequency is epsilon close with probability at least 1 minus gamma. This big enough value is still polynomial in size of the domain of P, 1 by epsilon and 1 by gamma. So this is efficiently PAC learnable. We can extend this idea in the case of learning task system with no hard task. We'll do the following. For all tasks, we schedule the task when a job of this task is active till we collect enough samples of interarrival time and computation time. Then we approximate the interarrival time and computation time distributions. So we execute the task system for a polynomial number of steps and collect enough samples to infer epsilon accurate approximations of the distribution with high probability. So the task system with only soft tasks are efficiently PAC learnable. Indeed, in our experiment, the distribution of a task system with soft tasks can be learned efficiently with a small number of samples. Here, EXC and ARR refers to the distributions of the computation times and the interarrival times respectively. The x-axis is the number of time steps over which the system is executed. The y-axis on the right corresponds to the number of samples collected over a duration of time when the system executes. Note that not every job that arrives in the system can be executed until completion. Therefore, over time, we get more samples for interarrival time compared to samples for computation time. Here, the left y-axis is the max norm distance between the probabilities in the actual distributions and the learned distribution across all subtasks. We can see that with more training, we are learning the distributions more accurately. To safely learn a system, the learning algorithm must ensure that all the jobs of the hard task meet their deadlines. So we have to follow a safe scheduling strategy while learning. Under this safe schedule, we will observe enough samples for the hard task, but we may not observe enough samples for soft task. We thus need stronger conditions in order to be able to learn the distributions of the soft task while ensuring safety. The good for sampling condition states that for all soft tasks I, the safe region contains a state Vi where a new job of task I enters the system and there exists a strategy sigma I that safely schedules the hard task, and under this sigma I, this new job is guaranteed to finish before deadline. We proved that this guarantees enough samples for the soft task. So this is a sufficient condition for safe back learning. But in this case, we cannot bound the time needed to get the next sample in the learning algorithm by a polynomial. So it doesn't guarantee efficient back learning. We now give a more restrictive condition to guarantee efficient back learning. This condition is as follows. For all soft tasks, there is a set of scheduler vertices safe I in the safe region such that for all safe I, there is a strategy under which all hard tasks and the task I can be safely scheduled. And there is a safe strategy sigma I for the hard task such that from any state in the safe region, safe I is reachable within k steps using sigma I. This k is bounded polynomially in the size of the task system. We proved that this is a sufficient condition for safe and efficient back learning. Consider this task system as an example with one hard and one soft task. In this system, we do not have a safe schedule that can ensure the soft task never misses the deadline. Hence, the set safe2, that is the set from where we can safely schedule the hard task and the soft task, is empty. So good for efficient sampling condition doesn't hold. But always at time 12n plus 6, we can check that the system is at the same state. In this state, a new job by the soft task enters the system, and the next arrival time for the hard task is still 2 time unit. So from this state, the new job of soft task can be scheduled and guaranteed to finish under a safe strategy. So the good for sampling condition holds. Once we have learned the model, we can compute a safe near optimal scheduling strategy. Given beta and gamma, we calculate an appropriate epsilon, which would be a function of beta, gamma and minimum probability in the system. Then we learn an epsilon closed system with high probability. Suppose we compute the optimal safe scheduling strategy sigma from the learned system. As the structure of the learned model is safe as the original one, in the original model also sigma would ensure that no hard task would miss the deadline. Also we get that with high probability in the original task system, expected mean cost for sigma is beta close to the optimal expected mean cost. Going back to the experiments, we report the value of the optimal expected mean cost as computed by Storm on the learned model as a function of the number of steps we use in learning. This result shows that our approach is effective in terms of the quality of learning and the number of samples required. The challenge is that the size of the MDPs are too large for exact model checking techniques even if we have 3 or 4 tasks. For this we resort to receding horizon framework. Here we fix a horizon h and we try to find the best action in the unfolding tree of the MDP of depth h. In particular, we use the Monte Carlo tree search or MCTS algorithm. It builds the search tree incrementally by selecting and adding a new node to the tree in every iteration and getting an estimation how good that node is by simulation. During the selection and simulation phases, we use advice that prunes parts of the MDP on the fly in order to ensure that only safe schedulers are explored. One of the most successful model-free learning algorithm is the Q-learning algorithm. It is used to learn near optimal strategies in an MDP for the discounted sum objective. In our scheduling problem, we search for near optimal strategies for the mean cost and not for the discounted sum. However, if the discount factor is close to 1, both values coincide. We use an implementation of deep Q learning available in the OpenAI repository which uses a neural network to learn the Q values. We use shielding, a technique that restricts action in the learning process so that only those actions that are safe for the hard task can be used. We use two kinds of scheduler strategies as the advice in MCTS and for shielding in Q learning. In the earliest deadline first or EDF strategy, it always schedules the jobs by hard task with earliest deadline. If there is no job by any hard task, then only it allows all job by soft task. This is easy to compute and can be applied to larger systems, but it is too restrictive. On the other hand, we have the most general safe scheduler that allows all safe edges for a scheduler vertex in the MDP. While this allows us for maximum exploration as it leaves open all possible safe scheduling solutions, but it needs to be pre-computed to be used. We use the tool called Absinthe to compute this. In this table, we compare values obtained by MCTS and DeepQ learning. While DeepQ learning provides good results for small task systems with 3 or 4 tasks with several thousand of states, this method doesn't perform well for benchmarks with large number of tasks. In those cases, the state space was found to be too large to learn a good strategy, and the output produced a cost much higher than that observed with MCTS. This ends the talk. Thank you for your attention.
Okay, thank you for the presentation there, Braj. Okay, do we have any questions? You can use the Q&A or you can raise your hand as before. So let me start with a question. So I gathered from near the end that you have you split it into two phases. You were learning the model first, and then you were kind of solving for optimality. Can those parts of the process be interleaved to some extent, as you might do with some approximate methods for MDPs? So you're learning the optimal policy here, scheduling, and learning the values at the same time. Can that be done here?
Yeah, possibly, but in this case we have not tried that.
Sorry, you're a little quiet. Can you
can you hear me?
Just, but you're quite quiet.
Yes, I mean it can be possibly done, but in this case we have not tried.
Okay. So meanwhile, we have another question from Kushraj Madnani. The question is, did you also consider models where jobs are not preemptive?
No, not in this case.
Okay. Do you think that would change your method radically, or could it be integrated potentially?
possibly it would be difficult. I mean, in this case, the MDP will be different. So in this case also we can construct the MDP and do the same thing. So yes, so it would also work.
Okay. I don't see another question yet. So yeah, one last small question from me. So you seem to be using a kind of long run average objective. You're trying to minimize the cost over the whole duration of the scheduling problem. But in the end, you switched to a finite horizon, or you truncated the horizon. So how do those two things connect?
So in practically, it is still working fine because in our cases, the MDP, the tasks that are scheduled needs to be completed before a deadline. So we do not really need a large horizon to get the average value. And in general, theoretically, for mean payoff, for average mean payoff, we can show that there exists a big horizon such that instead of just doing average mean payoff, if we do a finite total payoff for, we try to optimize total cost for a finite horizon, it still work for a if we try for a big horizon in practical.
Okay, thank you. Okay, last chance for any more questions. Okay, I don't see more questions. So thanks again for the presentation, Debraj. And thanks to all three speakers in this session. Very nice presentations. Hopefully if you have further questions for the authors about their work, you can catch them on GatherTown later in the conference. But for now, this session is wrapping up. So thank you very much.